This is Theorem 13. So you only have 3 geometry proofs that you actually have to have this format for. So these are your 3 theorems where you'll have to go through your given to prove, construction and proof. I can't remember if I said it in the last video. I'm pretty sure I said it in the first one. Theorem 11, the converse is true. Theorem 12, the converse is true. And this theorem here, the converse will be true also. So it just means the reverse of the statement is also true. You can use it backwards and forwards. So don't be afraid to do that if you're given, just a normal geometry question and they're like, oh, prove this triangle is equal to this triangle. Use this stuff backwards and forwards. Right, so given. What was I given in the question? I was given 2 similar triangles, A, B, C and D, E, F. I'm going again, get my drawings. I'm going to make A, B, C a bit bigger. I'm not making them isosceles or anything like that. I'm just drawing 2 similar triangles. And labeling them. A, B, C. And D, E, F. So there we are. A, B, C, D, E, F. Similar. I need to put in the markings that just show they're the same. Whatever way you want to do that. Or you could, obviously, instead of the tick, do 3 little lines. Whatever you want to do. So what was I given? I was given 2 similar triangles. I have called them A, B, C and D, E, F. I am going maybe to go a little bit faster because I think hopefully you should have a little bit more of the idea of where I'm getting all this information. What am I trying to prove? I'm trying to prove their sides are in proportion. So I'm trying to prove that AB over DE is equal to maybe AC, whatever way you want to do this, over DF, and that's equal to BC over EF. Doesn't matter if you start with the big triangle or the small triangle, because it's just trying to show the sides are in proportion. It's a very flexible rule, but you have to go in order. Construction. I'm going to draw a triangle onto, well, it's like I'm not really doing that, but it's like I'm picking up this triangle and putting it on here. So I'm going to assume that this triangle here is smaller than this one. Okay, that's, I mean, obviously it could be the other way around. This one could be the smaller one. ABC could be smaller than DEF, but the way I've drawn it, DEF, so the triangle DEF is smaller than the triangle ABC. Maybe that sounds ridiculous, but I need to be as clear as possible. Okay, I need to mark off a point then on AB, and I need to mark off another point on AC, and the point that I mark off has to be the same, create the same length as DE and create the same length as DF. So it's pretty much as though I'm picking up this triangle and putting it on here, but I'm not able to do that. So what I'm saying is I'm marking a point X on AB such that AX, the length of AX, is equal to the length of DE. This is a very long way around of saying I'm pretty much just drawing the same triangle on top of this one here. And then I need to mark a point, so we're doing the exact same thing again. Mark a point Y on, better marking that I'm calling this Y, on AC. Such that Y is equal to DF. I just need to connect them with a ruler. And then draw XY. Okay. Proof. So AXY is congruent to the DEF. So they are the exact same triangle. How do I know that? That angle is the same as that angle. That side is the same as that side, and that is the same as that side. So I'm just going to go for angle, side angle there. No, side angle, side, sorry. Right, so then that means that the angle AXY, the one that's here, is equal to the angle ABC. So those two are the same. How do I know that? Well, if those two are equal and these two triangles are similar, then those two have to be the same. Therefore, you know, if you have corresponding angles, you have parallel lines. If you have parallel lines, you have corresponding angles. If you have corresponding angles, you have parallel lines. So XY is parallel. Sorry, not coming down far enough here. XY is parallel to BC. And the reason that I know that is I have corresponding angles. Now, from Theorem 12, if you have a line parallel to BC and cuts AB in the ratio of S to T, then it also cuts AC in that same ratio. So I know that the length of AB over the length of DE is equal to AC over DF. You know, look at your diagram and sorry, no. I know, okay, so the length of AB over AX, so this is from Theorem 12. The length of AB over AX is equal to AC over AY. AB over AX is the same as AC over AY. And that's going back to Theorem 12. It's meant to be an AX. It's meant to be AY. And that's from Theorem 12. And you can just write what Theorem 12 states. You know, line parallel to BC cuts AB in the ratio of ST, then it also cuts AC in that same ratio. Now, but AX is the same as DE, so therefore, but the length of AX is the same as the length of DE. We've met it that way. That's from our construction. And same with the other one, AY is the same as DF. Med them that way. So that just means that AB over AX, which that's the same as AB over DE, is going to be the same as AC over DF. And you don't have to do the whole thing again, but you could have picked up the triangle and put it on here and had that, you know, be the top of your triangle, let's say. So we don't have to do all of it again. We can just say similarly. I could have done it a different way. I know I didn't pick up the triangle, but that's what I was pretty much doing. So similarly, we could have, you know, done our construction a different way, and we would have had the length BC over EF is the same as AB over DE, which just implies AB over DE is the same as AC over DF, which is the same as BC over EF.